Let's solve the following system using Gauss-Jordan elimination. Our first step in solving this system is to set up the augmented matrix for the system. So it might help to label our columns X, Y, and Z just to help us put the coefficients in correctly. And over on the right side of our vertical bar, we'll have the numbers, the constants from the right sides of the equations. So our first equation is going to translate into 2, -4, 15, 20. So notice that if we have something like -4y, our coefficient then is really a negative number. We're getting the coefficient -4 in our matrix. Now, to solve using Gauss-Jordan elimination just means getting this matrix, the left side of this matrix, into reduced row echelon form using our row operations. So first step will be to get a 1 in the upper left-hand corner. Probably the easiest way to do that is to swap rows. So let's swap rows 1 and 3. And that way we've got a nice leading 1 in the upper left-hand corner. Now next step will be to use this leading 1, or we can refer to it as a pivot, use this pivot to get zeros in the rest of that column. So we're going to need to get rid of the 1 and the 2 here. Let's do row 2 minus row 1. So our operation when we're trying to eliminate a number is always to do the row that we're on plus or minus a multiple of our pivot row. And if we're trying to eliminate a 1, then the correct multiple would be -1. If we're trying to get rid of a 2, we'd have to do the row that we're on minus 2 times our pivot row. And again, pivot row, just a shorthand for saying the row that contains our leading 1 that we've got in that column there. So first row is not going to change. And if we do row 2 minus row 1, we're going to get 0. -2 minus -2 is going to be 0. 7 minus 4 will give us 3. And 9 minus 3 is going to give us 6. Now down in our bottom row, if we do row 3 minus 2 times row 1, we're going to get 2 minus 2 is 0. -4 minus 2 times -2 is going to give us 0. And then we'll have 15 minus 8 gives us 7. 20 minus 6 will give us 14. So that is the first column all dealt with. We got our leading 1 and we used that leading 1 to get zeros in the rest of that column. So now we're going to move down into the right and try to get a leading entry for our second row. And if we think for a minute about how we could make this entry here equal to 1, well, multiplying the row by any number is not going to change this value. And swapping rows is not going to work so well either. Swapping with the bottom row isn't going to help us. And swapping with the top row will undo all this nice work that we've already done in column 1. Similarly, if we take this row and we add on a multiple of another row, it's either not going to work or it's going to undo our work in column 1. So what we really need to do is move further over to the right. The first non-zero entry that we can get is in the third column. So in this situation where we can't make this entry equal to 1, at least not without undoing work in the previous column, the rule is to move further right when you're trying to create a 1 there. So let's move further right over into the third column, and we're going to choose this 3 to become our next leading 1. So let's take row 2 divided by 3. That's going to give us 0, 0, 1. and then a 2, and we'll leave the other 2 rows alone for now. Okay, so that gives us now a pivot for the third column, and we're going to work on getting zeros in the rest of that column. So we're going to try to get rid of this 4 and the 7. So to do that, let's take row 1 minus 4 times our pivot row, and at the same time we can do row 3 minus 7 times our pivot row. All right, so that's going to give us 1, -2, and 0. And over on the right side, we'll have 3 minus 8 gives us -5. Second row won't be changing. And our third row then, if we do row 3 minus 7 times row 2, we're going to get 0, 0, 0. And then finally over on the right side, we get another 0. 14 minus 14 gives us 0. So let's take a look at our leading non-zero entries. In the first row, the first non-zero entry that we see is this 1 here. And in the second row, the first non-zero entry that we see is over here. So all of our leading non-zero entries are 1s. These leading ones do have zeros everywhere else in their columns. The leading ones do move down into the right. And we do have a 0 row, which is located at the bottom of the matrix. So this matrix is now in RREF. It's in reduced row echelon form. So we are done the matrix part of the problem. Now, all that remains is to figure out how to write down our answer. So let's remember that these columns here represented X, Y, and Z. And over on the right side, this last column just represents our numbers. To start talking about our solution, what we're really interested in is any columns here that don't have leading 1s in them. The column for Y does not have a leading 1 in it. So we're going to write y equals k. This k here is called a parameter, and this represents the fact that y can be any real number. If there's no leading 1 in the column for y, then we're not going to be able to solve these equations for y, and that means that y is unrestricted. So y can be any real number. The way we notice that is that there's no leading 1s in its column. So remember, we identified the leading 1s earlier by looking at the rows. We found the first non-zero entry in each row, and we circled those. But in writing down the solution to the system, it's really the columns that do not contain leading 1s that are going to be of the most interest to us. So we've got y equals k, y is equal to a parameter. So this solution is going to have 1 parameter in it. Now we will be able to solve for x because we do have a leading 1 in the column for x. So if we focus on that top row, it's saying that x minus 2y plus no z's is equal to -5. So if we rearrange this a little bit, x is equal to -5 plus 2y. And remember that y is equal to k. So that tells us x is equal to -5 plus 2 times k. Okay, the column for z has a leading 1, so that tells us that we will be able to solve for z. If we look at this second row here, that equation there is saying that z, 1 times z, is equal to 2. And we can now put these 3 facts together and write down the solution to our system. So we would say, as an ordered triple, x, y, z is equal to -5 plus 2k is our value for x. Our value for y is k. And our value for z is 2. And we can just remind ourselves here, k represents any real number. So this is an example of a system with infinitely many solutions. For any value of k that you choose, you get a specific or particular solution to the system. So you could try plugging in some of your favorite k values and checking that those ordered triples do provide solutions to the system. Just as a side note here, notice that we did have a row of zeros down in the bottom of the equation. That equation there simply gave us no information. So it doesn't contribute in any way to our solution. It's really just saying 0 is equal to 0, which is a fact that hopefully was already obvious to us. This next example will give us a little bit more practice with writing down the solution when we do have infinitely many solutions to a system. We're going to circle the first non-zero entry in each row. So there they are. Bottom two rows of the matrix are 0. And the fact that the W and the X have leading ones in their columns means we will be able to solve for W and X when we're writing down the solution to this system. But Y and Z have no leading ones in their columns. So let's point that out first. There's no leading ones in these two columns. That means Y and Z are going to be free to take on any real number values. And the way that we express that quickly using mathematical notation is just to give them a parameter. So just give them a new name to represent the fact that they're free to take on any values. So you could use k. Often if there's multiple parameters, we'll use a and b, for example. So let's say y is equal to a, z is equal to b. Any real numbers, and they certainly don't have to be the same real number, so that's why we use two different letters there. Now once we've decided on that, we can go ahead and figure out what w and x should equal. So from the first equation, w plus 3z is equal to 8, and if we rearrange that, w is equal to 8 minus 3z, and using the fact that z is equal to b, we get w is equal to 8 minus 3b. Looking at our second row, we can say x minus y plus 4z is going to equal 2. If we solve this for x, we've got x is equal to 2 plus y minus 4z. And now we're going to use the fact that y is equal to a and z is equal to b to rewrite this. So x is equal to 2 plus a minus 4b. And that way we've got our values of w, x, y, and z all in terms of our two parameters. Notice that these bottom two rows here, they give us no information. They simply say 0 equals 0. Which is a fact that's true, but irrelevant to our solution to the problem. So our final answer here, if we want to write wx, yz, we said w is equal to 8 minus 3b, x was 2 plus a minus 4b, y is equal to a, z is equal to b. And just to be clear here, we'll say a and b can be any real numbers. So normally, if you're working with a graphing calculators will give you the reduced row echelon form. So they'll give you this kind of output in matrix form, but it's still up to us to do the last part of the math here to actually be able to write down the solution in a way that's meaningful to us.